This video showcases 5 examples of integration by parts. Check how the integrals are determined here in integral calculus. The first example includes the integral of y cubed dy over the square of the quantity y squared plus 6. Place the denominator up to have the integral of the quantity of y squared plus 6 raised to negative 2 times y cubed dy. With integration by parts, consider u as y cubed, and du is taken as 3y squared dy. The remaining part of the integral is considered dv, that is, the quantity of y squared plus 6 raised to negative 2 dy. First is to check if the term can be integrated, so use y squared plus 6 as u, and its du is 2y dy. With y from du, the term cannot be integrated for the moment due to a missing y. To integrate dv, break the terms completing dv. So the integral now becomes y squared times the quantity of y squared plus 6 raised to negative 2 times y dy. Let's check it again if dv can be integrated. U is y squared with du as 2y dy. dv is then the quantity of y squared plus 6 raised to negative 2 times y dy. Check it for integration. U is y squared plus 6, and du is 2y dy. This time, we have y dy in the integral, so we only needed to adjust it with 2. So with the integral, multiply 2 with y dy and place 1/2 before the integral. And through general power formula, we can have v as half of y squared plus 6 raised to negative 2 plus 1 over negative 2 plus 1. Now we determine v as negative 1 over 2 times y squared plus 6. Having u, v, and du already identified, we can proceed to integrating by parts using the formula. Start with uv, that is y squared times negative of 1 over 2 times y squared plus 6, minus the integrand of v, which is negative 1 over 2 times y squared plus 6, then multiply this with du, which is 2y dy. Simplify this first as negative of y squared over 2 times y squared plus 6 plus half of the integral of 2y dy over y squared plus 6. Again, check if the second term can be readily integrated. So have u as y squared plus 6, and du is 2y dy. Note that the numerator is the exact derivative of the denominator, so the second term can be integrated using logarithmic method. Thus, we get negative y squared over 2 times y squared plus 6 plus half of ln of y squared plus 6 plus c. Example 2 is to integrate the square of ln y dy. Integration by parts of a single term is still possible as long as we assign dv as 1 dy. So u is the square of ln y, and du becomes twice of ln y times 1 all over y with dy. Again, dv is 1 dy, and v is then cleared as y. Completing all parameters, use the formula for integration by parts. Starting with uv as the square of ln y times y, then subtract the integral of v du, which is y times 2 ln y dy upon y, where y's cancel out, simplifying the binomial as y times the square of ln y minus 2 times the integral of ln y dy. At this point, Again, complete the parameters. U is ln of y and du is dy over y. dv on the other hand is 1 dy and v is y. With all parameters present in the premise, proceed to the second integration by parts, then having the first term as is, with y times the square of ln of y minus twice of the second uv of y ln y minus the second integral of v du, which is y times dy over y. Y's cancel out once more, and the third term is integrated using simple power formula. Finally, the integral of the square of ln y is y times the square of ln y minus 2y ln y minus y plus c. Next is to integrate y raised to 8 times the square root of 4 plus 3y raised to 5 dy. Let's consider u as y raised to 8, and its du is 8y raised to 7 dy. dv is the remaining term square root of 4 plus 3y raised to 5 dy, which can be written as the quantity of 4 plus 3y raised to 5 raised to 1/2 dy. Check if the term is readily integratable. Taking u as 4 plus 3y raised to 5, du is 15y raised to 4 dy. With y raised to 4 present in the derivative, the term cannot be integrated now, as there are missing y's. What we can do is to extract y raised to 4 from the first term of the original integral, and place it as a part of the derivative. So the integral now becomes y raised to 4 times the square root of 4 plus 3y raised to 5, then the new derivative becomes y raised to 4 dy. Back at the start, u is now assigned as y raised to 4, and du is 4y cubed dy. dv is the quantity of 4 plus 3y raised to 5 raised to 1/2 times y raised to 4 dy. Let's check the second term's integral again. U is 4 plus 3y raised to 5, and du is 15y raised to 4 dy. Y raised to 4 is already in the integral, so we only need to adjust it with the constant 15. So adjust the integrand by multiplying 15 to the derivative and 1 over 15 before the integral. Then integrate dv using general power formula to have v as a 15th of the quantity 4 plus 3y raised to 5 raised to 1/2 plus 1 over 1/2 plus 1. This is simplified as 1 over 15 of the quantity 4 plus 3y raised to 5 raised to 3/2 over 3/2. So v is now taken as 2 over 45 of the quantity 4 plus 3y raised to 5 raised to 3/2. Now proceed to integration by parts, where u times v becomes y raised to 4 times 2 over 45 times the quantity of 4 plus 3y raised to 5 raised to 3/2, and then the integral of v du is 2 over 45 times the integral of the quantity 4 plus 3y raised to 5 raised to 3/2 times 4y cubed dy. Simplify the terms and get 2y raised to 4 over 45 times the quantity of 4 plus 3y raised to 5 raised to 3/2 minus 8 over 45 times the integrand of y cubed times the quantity of 4 plus 3y raised to 5 raised to 3/2 dy. The term in the integrand is still a product, so let's attempt to use integration by parts again. U is y cubed, and du is 3y squared dy. dv is the quantity of 4 plus 3y raised to 5 raised to 3/2 dy. Then we take v. First, check that in the integral, u is 4 plus 3y raised to 5. du is 15y raised to 4 dy. The derivative still has y raised to 4, but then the integral only has y cubed to offer. So this is the end of the solution, and we can say that the function cannot be integrated. Example 4 looks for the antiderivative of y raised to 4 times sine of y squared dy. Take y raised to 4 as u, and du is 4y cubed dy. dv is sine of y squared dy. Check that to integrate dv, u is y squared and its du is 2y dy, where we are missing y, so extract 1y from the first term. So we adjust the integral into y cubed times sine of y squared with y dy. Again, use y cubed, and du is 3y squared dy. dv is sine of y squared dy, where its u is y squared and du is 2y dy. This time, we have y in the integrand, so we only need to adjust dv by multiplying 2 to the derivative and 1/2 before the integrand, and then proceed with the trigonometric integration to find v as half of negative cosine of y squared, simplified as v equal to negative cosine of y squared over 2. Knowing u, v, and du, proceed to integration by parts, starting with uv as y raised to 4 times negative cosine of y squared over 2. Then subtract the integrand of v du, which is negative cosine of y squared over 2 times 4y cubed dy. Simplify 4 and 2, then place the constant out of the integrand, and work with another set of parameters as the integrand has a product. So we attempt to work on another integration by parts. U this time is y cubed, and du is 3y squared dy. dv is cosine of y squared dy, and v is sine of y squared times 2y dy. We are missing y in the integrand, so we extract a y in the first term again. Extract 1 from the second term and get the same first term, negative y raised to 4 times cosine of y squared over 2, but the second term now is twice of the integral of y squared times cosine of y squared with y dy. Complete the parameters now. U is y squared and du is 2y dy. dv is cosine of y squared times y dy. Check if these can be integrated. U is y squared and du is 2y dy. The only thing we need to adjust now is to place 2 with y dy and 1/2 before the integrand, integrating dv and having v as half of sine of y squared. With u and v already identified, let's have the second integration by parts, where the first term remains the same and we work on 2 times the integral of y squared cosine of y squared times y dy. This is expanded into uv of y squared times half of sine of y squared minus the integral of half of sine of y squared times 2y dy. 2 and 1/2 cancel out, simplifying the long solution as negative y raised to 4 with cosine of y squared over 2 plus y squared sine of y squared minus the integral of y squared with 2y dy. The last term with integral can be simplified using simple power formula, which can add to the long answer by cosine of y squared plus c. The last example contains the integral of y squared e raised to 3y dy. Check the parameters and have u as y squared. du is 2y dy. dv is e raised to 3y dy. Then solve for v. The u in dv is 3y, and its du is 3 dy, so we needed 3 in the derivative. Adjust the integrand and have 1/3 of the integral of e raised to 3y times 3 dy. So dv is integrated as v, which is equal to 1/3 of e raised to 3y. Then integrate by parts. uv is then y squared times 1/3 of e raised to 3y minus the integral of 1/3 of e raised to 3y times 2y dy. Take out constants and have a third of y squared e raised to 3y minus 2/3 of the integral of e raised to 3y times y dy. Having a product in the integral, this is a sign that there is another integration by parts to happen. So take u as y, and du is dy. dv is e raised to 3y dy, and v was solved earlier as a third of e raised to 3y. With everything complete, integrate the function the second time, coming up with minus 2/3 of uv, which is a third of e raised to 3y, minus the integral of a third of e raised to 3y dy. Place constants out and have a third of y squared times e raised to 3y minus 2/9 of y times e raised to 3y plus 2/9 of the integral of e raised to 3y dy. Check the last term with the integral. This can be integrated using logarithmic method. So u is 3y and du is 3 dy. We are missing out 3 in the derivative. So adjust the third term by injecting 3 and 1/3 in the term to have the final derivative as a third of y squared times e raised to 3y minus 2/9 of y times e raised to 3y plus 2/27 of e raised to 3y plus c.